The afternoon sun cast long shadows across the proving grounds at Kummersdorf, Germany, on a February day in 1943. Inside the captured American tank designated War Daddy 2, Hauptmann Klaus Richter wiped sweat from his forehead despite the winter chill. He'd been testing this Sherman for 3 hours now, and something didn't make sense. The fuel gauge, the maintenance manual they'd translated, the way the engine responded, all of it pointed to one impossible conclusion. "Check the fuel sample again," Richter ordered his mechanic, Obergefreiter Hans Müller. "There must be an error." Müller climbed down from the tank, holding a small vial of liquid up to the light. "It's gasoline, Herr Hauptmann. Just as it was an hour ago, standard petrol, nothing unusual." Richter stared at the captured intelligence documents spread across a makeshift table. Reports from Tunisia spoke of Shermans running on diesel. Different reports mentioned radial aircraft engines. Others described massive Veit automobile motors. The British had sent photographs of Shermans with completely different engine configurations. It was as if the Americans were fielding 5 different tanks under the same name. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Hauptmann Richter couldn't comprehend that cold February afternoon would become one of the most profound revelations about American industrial capacity during World War II. The Sherman wasn't just a tank. It was a statement about a nation that approached warfare not with Prussian precision, but with something far more unsettling: industrial flexibility on a scale Germany had never imagined possible. This is the story of how German engineers tested captured American tanks and discovered something that shattered their understanding of modern warfare. It's about the moment when German tankers realized they weren't just fighting an enemy with better resources. They were fighting an enemy that had solved the problem of logistics in a way that made traditional military thinking obsolete. By February 1943, the tide of war had shifted dramatically from Germany's early blitzkrieg victories. The Wehrmacht had tasted defeat at Stalingrad, the Afrika Korps was collapsing in Tunisia, and for the first time, German intelligence officers were getting their hands on significant numbers of American tanks. The Waffenamt, Germany's weapons testing agency, had established protocols for evaluating captured enemy equipment since the war's beginning. They'd tested French tanks after the fall of France in 1940. They'd analysed Soviet 34 tanks captured during Operation Barbarossa. They'd studied British Matildas and Crusaders from the Western Desert. But nothing had prepared them for the Sherman. The first M4, A1 Sherman to reach Kummersdorf arrived in late January 1943. Captured from the 1st Armoured Division near Spatla, Tunisia, on February 22 by Panzerabteilung 501, the tank had been driven 350 kilometres to Tunis over 4.5 days. It was then shipped to Germany for extensive evaluation at the Army Weapons Office proving grounds. The testing protocols were rigorous. German engineers measured armour thickness at multiple points, stenciling the results directly onto the tank's hull. They fired captured American ammunition through the 75mm gun to assess accuracy and penetration. They tested mobility, reliability, ergonomics. Every aspect of the Sherman was documented with Germanic thoroughness, but it was the engine compartment that first sparked confusion. The captured War Daddy 2 mounted a Continental R975 radial engine, a 9-cylinder air-cooled powerplant originally designed for aircraft. It produced 400 horsepower and ran on standard gasoline. The German mechanics found it remarkably accessible for maintenance, far easier to service than the Maybach engines in their Panzer IIIs and IVs. Then reports arrived from other testing centres. A Sherman captured by the 15th Panzer Division featured an entirely different engine, a pair of GM Detroit Diesel 671 two-stroke inline engines. This M4A2 variant ran on diesel fuel. It produced 375 horsepower from what was essentially 2 truck engines mated together. "How is this possible?" demanded Oberst Friedrich Weber, chief of the Captured Vehicles Assessment Section. "The Americans are using completely different fuel systems in identical tanks?" The confusion deepened when intelligence officers translated captured American field manuals. The documents described not 2 Sherman variants but 5 distinct models, all in active service simultaneously. The M4A1, identical except for a fully cast upper hull, also using the Continental radial. The M4A2, fitted with twin GM diesel engines. The M4A3, mounting a Ford GAA Vate gasoline engine, an 18-litre aluminum block powerplant producing 450 horsepower. The M4A4, equipped with the Chrysler A57 multibank engine, a frankly bizarre 30-cylinder radial engine constructed by gearing together 5 Chrysler inline 6-cylinder automobile engines. "This is madness," Weber told his staff during a briefing in March 1943. No rational military would field 5 different engines in what is supposed to be a standardized tank. The logistics alone would be catastrophic. He was thinking like a German officer, trained in the Prussian tradition of standardization and meticulous supply planning. The German military had spent years developing the Panzer IV, carefully refining its Maybach engine and transmission. When production increased, they increased production of the exact same components. Quality control, standardization, efficiency through uniformity. The Americans had done something that seemed to violate every principle of military logistics. They'd designed a tank that could accept 5 completely different engines, and they were producing all 5 variants simultaneously. What Weber and his colleagues couldn't grasp was that this apparent chaos was actually genius. The M4 Sherman's development had begun in earnest in 1941, when the United States Army recognized the M3 Lee medium tank as an interim solution at best. The Sherman's designers, working at the Aberdeen Proving Ground in Maryland, made a fundamental decision that would define American armor production for the rest of the war. They designed the tank to be modular, the engine compartment, transmission, drivetrain. These could accommodate different power plants with minimal modification to the basic hull design. The turret ring remained constant. The suspension system was standardized, though it would evolve from vertical volute spring suspension to the improved horizontal volute spring suspension later in the war. The 75mm gun remained the same across all early variants. This modularity was born from necessity. In 1941, America's industrial mobilization was just beginning. The nation that would eventually produce nearly 50,000 Sherman tanks didn't have 50,000 of any single engine available. The Continental Ir-975 radial engine was an aircraft powerplant. American bomber and fighter production needed those engines desperately, so the Army Ordnance Department did something revolutionary. They went to Detroit and asked the automotive industry a simple question. What engines do you have available right now that could power a 30-ton tank? General Motors offered the 6046, essentially 2 of their truck diesel engines. Ford had been working on a massive V12 aircraft engine that had been cancelled. They proposed an 8-cylinder version, the GAA. Chrysler, operating the Detroit tank arsenal, created the A57 multibank by clustering 5 car engines together. Each solution was different. Each solution worked. But the logistics. German planners protested when analyzing captured intelligence. How do they supply fuel? How do they train mechanics? How do they stock spare parts? The answer revealed something profound about American versus German approaches to warfare. Germany had bet on quality through standardization. Their tank development philosophy emphasized creating the best possible vehicle, then producing it in quantity. When the Panther tank entered production in 1943, it mounted a single engine type, the Maybach HL230 P30. Excellent engine, tremendously powerful, also tremendously complex and impossible to produce in the quantities needed. America bet on quantity through flexibility. They recognized that in a global war, perfection was the enemy of good enough. A Sherman with a reliable Continental radial was excellent. A Sherman with a reliable Ford Vate was equally excellent. A Sherman with GM diesels? Also excellent, particularly for the Marine Corps, who preferred diesel fuel for safety reasons aboard ships. The supply chain adapted accordingly. Gasoline-powered Shermans generally went to units fighting in Europe, where gasoline supply lines were already established for trucks and other vehicles. Diesel-powered M4A2S went to the Soviet Union under Lend-Lease and to the US Marine Corps in the Pacific, where Navy logistics could supply diesel fuel from ships. The British received a mix of both. Field maintenance became simpler, not more complex. Each Sherman variant came with detailed technical manuals specific to its engine type. Mechanics trained on Continental radials stayed with units equipped with those tanks. Ford GAA mechanics went with M4A3 units. The engine modularity meant that in depot-level maintenance, if necessary, an entire engine could be swapped out quickly rather than attempting complex repairs in the field. But there was something else happening that German intelligence officers found even more disturbing when they pieced together the full picture. The Americans were outproducing Germany at a rate that made standardization irrelevant. By the time Hauptmann Richter sat in War Daddy 2 at Kummersdorf, American factories were producing Shermans at a rate of over 2,000 per month. Chrysler's Detroit tank arsenal alone could produce up to 800 M4A4S monthly by mid-1943. Fisher Body, Grand Blanc Arsenal, Ford, Pacific Car and Foundry, Federal Machine and Welder, Pressed Steel Car Company, Baldwin Locomotive Works, American Locomotive Company, and Pullman Standard, all were producing Shermans simultaneously. 11 plants, 5 different engine types, dozens of minor variations in components and assemblies, and somehow, impossibly, it all worked. The German testing reports from Kummersdorf tried to make sense of this. They praised the Sherman's reliability. German testers found the tank well built and comfortable, far easier to maintain than German tanks. The automotive components were superior to German equivalents in accessibility and reliability. One report noted that German crews actually preferred captured Shermans to their own Panzer IIIs and IVs for these reasons. A photograph from the testing shows Albert Speer, Reich Minister of Armaments and War Production, sitting in the commander's hatch of War Daddy 2. His face is contemplative. By that point, March 1943, Speer was trying desperately to rationalize German war production. He was consolidating factories, standardizing components, eliminating redundancies. The Führer demanded more tanks. German industry was straining to produce them. And here sat an American tank that represented everything German military doctrine said was wrong. Multiple engines, multiple fuel types, dozens of manufacturers, supply chains that should have been a logistical nightmare, yet the Shermans kept coming. German intelligence estimated that by June 1944, when the Western Allies landed in Normandy, approximately 16,000 Shermans were in service with American and British forces in Europe alone. Thousands more were fighting in the Pacific. Thousands more had been shipped to the Soviet Union. In comparison, Germany produced approximately 6,000 Panzer IVs during the entire war, about 6,000 Panthers, fewer than 1,500 Tigers of all types. The numbers weren't close. They weren't even in the same universe. Hauptmann Richter wrote in his report, "The Sherman's modularity reflects a production philosophy we cannot match. The Americans have solved the problem of mass production not through standardization of components, but through standardization of interfaces. Each engine mounts to the same transmission through the same connection points. This allows them to use whichever engines are available without redesigning the entire tank. It is ingenious, if crude. Crude, perhaps, but devastatingly effective." German tank crews who captured and used Shermans in combat reported something that Wehrmacht High Command found deeply unsettling. The tanks just worked. They didn't break down constantly like Panthers with their temperamental Maybach engines and fragile final drives. They didn't guzzle fuel like Tigers. They could be maintained by crews with basic mechanical skills, unlike the complex German tanks that required specialized training. One captured German tanker, interviewed after the Battle of the Bulge, where SS units had successfully used captured Shermans to breach American lines at Mannheim, stated, "The Sherman was a driver's dream. It didn't matter if it had the radial engine or the Vate. It started reliably. It shifted smoothly. It didn't leave you stranded. I would have traded my Panther for a Sherman without hesitation, if I'm being honest." This was the psychological impact that worried German commanders most. Their own tankers preferred the enemy's equipment, not because the Sherman had better armor. It didn't. Not because the Sherman had a better gun. Early models certainly didn't. But because the Sherman represented something more valuable than firepower or protection. It represented American industrial capacity to wage war at a scale Germany couldn't match. The 5 different fuel types weren't a weakness. They were a strength. They demonstrated that America could produce tanks faster than Germany could produce the fuel to power their more advanced designs. They showed that American logistics could handle complexity that would cripple the Wehrmacht's carefully planned supply system. By the summer of 1944, the reality of what those 5 different fuel types represented had become unavoidable to German commanders on the Western Front. June 6th, D-Day. American, British, and Canadian forces stormed the beaches of Normandy. Within weeks, thousands of Sherman tanks had poured into France. German intelligence officers tracking Allied vehicle registrations noticed something that should have been impossible. The Americans were replacing combat losses faster than Germany could count them. A Sherman destroyed on Tuesday was replaced by Wednesday. Sometimes 2 replaced it. The spare parts flowed. The fuel flowed, the ammunition flowed, and most unnervingly, the Shermans themselves kept flowing from a supply chain that spanned an ocean. General Feldmarschall Erwin Rommel, commanding Army Group B in France, wrote to his wife in July 1944, "The enemy's materiel superiority is so great that all our own operational planning is constrained by it. They have tanks and vehicles in quantities we cannot match, and unlike our tanks, theirs actually reach the battlefield in working condition." That last sentence reflected a truth that German logistics officers had been confronting since 1943. German tank production numbers looked impressive on paper, but the Panther tanks rolling off assembly lines in Germany broke down before reaching the front. Their complex Maybach engines required specialized maintenance. Their interleaved road wheels, designed for superior off-road performance, clogged with mud and froze solid in winter. Their transmissions failed after 100 kilometers. The Sherman's 5 different engines all shared one characteristic: they worked. The Continental radial was an aircraft engine, proven reliable through thousands of flight hours. The Ford GAA was based on automotive technology, simple and robust. The GM diesels were derived from truck engines that had logged millions of miles on American highways. Even the bizarre Chrysler multibank, 30 cylinders of automotive engineering clustered together, proved more reliable than German purpose-built tank engines. This wasn't by accident, it was by design philosophy. German tank designers approached engines as specialized military equipment. They designed engines specifically for tanks, optimizing for power-to-weight ratios and combat performance. This produced impressive specifications. It also produced engines that required specialized manufacturing facilities, specialized mechanics, and specialized supply chains. American tank designers approached engines as industrial equipment. They used proven commercial power plants adapted for military use. This produced less impressive specifications on paper. It also produced engines that could be manufactured in existing facilities, maintained by mechanics trained on civilian vehicles, and supplied through logistics networks that already existed. The difference became stark in the field. A Panther tank with a broken Maybach HL 230 engine required parts manufactured in Germany, shipped to the front, and installed by specialized mechanics. If those parts were delayed by Allied bombing, or if those mechanics were killed, or if the supply train was destroyed by fighter bombers, the Panther became a 45-ton pillbox. A Sherman with any engine problem could often be repaired using parts cannibalized from another Sherman, regardless of which variant it came from. The modular design meant transmissions, final drives, suspension components, all were interchangeable. A Continental radial could theoretically be replaced with a Ford GAA if supplies dictated it, though this rarely happened in practice. More importantly, if a Sherman was truly beyond repair, another would arrive to replace it within days, sometimes hours. German prisoners of war marched past Allied supply dumps in Normandy during the summer of 1944, reacted with visible shock. One captured soldier, witnessing mountains of supplies stacked along French roadsides, remarked to his American guards, "I know how you defeated us. You piled up the supplies and then let them fall on us." He was right. The war in Europe had become what the Germans called Materialschlacht, material battle. It wasn't won by superior tactics or better tanks or braver soldiers. It was won by the side that could deliver more steel, more fuel, more ammunition, more everything, to the battlefield faster than the enemy could destroy it. And America's ability to deliver was enabled by industrial flexibility that German military doctrine couldn't comprehend. Consider the fuel logistics alone. By August 1944, American forces in France were consuming roughly 400,000 gallons of gasoline per day. The Red Ball Express, a truck convoy operation that became legendary, used over 5,000 vehicles to maintain supply lines, from Normandy ports to the advancing front. Most of those trucks ran on gasoline. The Sherman tanks running on gasoline integrated seamlessly into this supply network. They used the same fuel as the trucks delivering their ammunition, the same fuel as the jeeps carrying their commanders, the same fuel as the ambulances evacuating their wounded. One supply chain, one fuel type for the entire mechanized force in that theater. Meanwhile, the U.S. Marine Corps in the Pacific operated differently. Navy ships could supply diesel fuel directly from their bunkers. The M4A2 diesel Sherman variant was perfect for island-hopping campaigns where fuel had to be brought by ship. The Marines used the same diesel fuel for their generators, their landing craft engines, and their tanks. Again, integration. Again, efficiency. The British received both gasoline and diesel Shermans under Lend-Lease. They distributed them according to their own logistics networks, placing diesel variants where diesel fuel was available, gasoline variants where petrol was plentiful. The flexibility allowed them to maximize what America was producing rather than constraining American production to match British preferences. The Soviet Union received over 4,000 M4A2 diesel Shermans. Soviet tank crews, accustomed to the diesel-powered 34, appreciated the familiar fuel type. Soviet logistics officers appreciated that they didn't have to create a separate gasoline supply chain just for American tanks. The Shermans integrated into existing Soviet fuel distribution networks, 5 different engine types, multiple fuel types, and somehow, globally, it all synchronized. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. What German logistics officers failed to understand, until it was far too late, was that American war production wasn't about building the perfect tank. It was about building enough good tanks fast enough that losing them didn't matter. This sounds callous. It was brutally pragmatic. American doctrine accepted that tanks would be destroyed in combat. German doctrine tried to build tanks so superior they wouldn't be destroyed. The American approach meant accepting higher loss rates, but having unlimited replacements. The German approach meant lower immediate losses, but catastrophic strategic vulnerability when those irreplaceable tanks were eventually lost. By 1944, the mathematics had become merciless. Germany produced 6,000 Panthers during the entire war. America produced nearly 50,000 Shermans. If the exchange rate was 8 Shermans lost for every Panther destroyed, a ratio often cited in German propaganda, America would still have tens of thousands of Shermans remaining after every Panther was gone. And America would build more Shermans tomorrow. Germany wouldn't build more Panthers. The factories were being bombed. The fuel was gone. The skilled workers were dead or conscripted. The 5 different engine types in the Sherman represented something the Wehrmacht had never planned for: industrial resilience through redundancy. When Allied bombing damaged the Continental radial engine factory, Sherman production didn't stop. The other 4 plants kept building engines. When aluminum shortages threatened Ford GAA production, Chrysler multibank and GM diesel production continued unaffected. No single point of failure could cripple American tank production. Germany had no such resilience. The Maybach factory produced engines for Panthers and Tigers. When it was bombed, tank production stopped. The specialized components, the precision machinery, the irreplaceable skilled workers, all represented vulnerabilities in a supply chain built on standardization without redundancy. Captain Richter, the officer who'd first tested War Daddy II at Kummersdorf in early 1943, found himself commanding a Panther battalion in the Ardennes forest in December 1944. His unit participated in the desperate German counter-offensive that became known as the Battle of the Bulge. On Christmas Eve 1944, his Panther broke down for the 3rd time in a week. The final drive had failed. Again. It was a common problem with the Panther, caused by the tank's weight exceeding what the transmission could reliably handle. His battalion had started the offensive with 42 Panthers. By Christmas, 18 were operational. 12 had been destroyed by enemy action. 12 had broken down and been abandoned. Richter stood beside his immobilized Panther, watching American supply trucks roll past a kilometer away on a captured road. "They'll have replacement Shermans here by morning," he told his gunner. "We'll be lucky if repair parts reach us by spring. If at all." He was remembering War Daddy II. The tank he'd tested nearly 2 years earlier. How simple the engine had been to maintain. How reliable the controls had been. How comfortable the crew stations had been compared to German designs. At the time, he'd written it off as crude American engineering. Now, standing in the snow beside his broken Panther, he understood. The Americans hadn't been crude. They'd been right. They'd understood something the Wehrmacht had missed. In a prolonged industrial war, the tank that reaches the battlefield in working condition beats the tank that's theoretically superior but perpetually broken. The tank that can be repaired quickly beats the tank that requires specialized parts. The tank that can be produced in 11 factories using 5 different engines beats the tank that can only be produced in 3 factories using 1 engine. Flexibility beat perfection. Availability beat superiority. Volume beat quality. It was a lesson learned too late. By January 1945, Germany's war production had collapsed. Allied bombing had destroyed key factories. Fuel shortages meant tanks couldn't reach at the front even if they were built. The synthetic fuel plants that had kept the Wehrmacht mobile were ash. The Ruhr industrial region was under siege, and still, American Shermans kept coming. German soldiers began calling the American war machine the arsenal of democracy, originally Roosevelt's phrase, but now spoken with bitter respect. They'd seen the supply dumps. They'd seen the endless columns of trucks. They'd seen knocked-out Shermans replaced overnight. They'd captured American supply documents and marveled at the quantities listed. Thousands of tons of ammunition, millions of gallons of fuel, spare parts inventoried down to individual nuts and bolts. One captured German document, found in February 1945 by American intelligence officers, contained an analysis of Allied tank production. The German intelligence officer who wrote it concluded, "The enemy's tank production cannot be stopped by military action. They produce tanks faster than we can destroy them. They produce fuel faster than they can consume it. They produce ammunition at rates that make our entire annual production seem trivial. This is not a war we can win through superior equipment or training. This is a war of factories, and we have lost it." The 5 different fuel types in the Sherman were just a symbol, but they symbolized something profound. A nation that approached total war as an industrial problem to be solved through flexibility, standardization of interfaces rather than components, and massive redundant capacity. The psychological impact on German soldiers who understood this was devastating. They were still fighting. They were still brave. Their tanks were, in many ways, technically superior, but they knew they were fighting an enemy that could replace losses indefinitely while they could not. The Panther was a better tank than the Sherman in a direct engagement, but by 1945, For every Panther fielded, the Americans had 50 Shermans. Quality didn't matter when quantity was 50-1. The war in Europe ended on May 8, 1945. Germany surrendered unconditionally. The Wehrmacht, which had conquered most of Europe in 1940 and 1941, had been ground down by material attrition. Soviet industry in the east, American industry in the west. Britain's sustained resistance. All had contributed to a war of production that Germany simply couldn't win. In the aftermath, military historians began analyzing what had happened. How had the United States, which had been militarily unprepared in 1941, become the dominant military power by 1945? The answer was complex. It involved everything from strategic decisions to tactical innovations to individual heroism. But at the core was something simple. America had learned to wage industrial war better than any nation in history. The Sherman tank, with its 5 different engines and multiple fuel types, became the symbol of that capability. It represented a manufacturing philosophy that prioritized production volume and logistical flexibility over engineering perfectionism. It represented a willingness to accept good enough in massive quantities rather than perfect in limited numbers. This philosophy had critics, both then and now. American tankers who faced Panthers and Tigers in combat certainly wished for better armor and bigger guns. Crews who died in burning Shermans would have preferred better protection. The Sherman earned grim nicknames. Ronson, supposedly because it lit the first time, every time, like the cigarette lighter. Tommy Cooker, from the German soldiers who fought them. But post-war analysis revealed something surprising. American tank crews in Shermans had lower mortality rates than German crews in Panthers or Tigers. The Sherman's reliability meant crews weren't trapped in broken-down vehicles. Its ease of escape meant crews could bail out quickly when hit. Its availability meant destroyed tanks were replaced immediately, spreading risk across multiple engagements rather than forcing the same crews to fight repeatedly in irreplaceable vehicles. And most significantly, the Sherman won, not because it was the best tank, because it was everywhere, supplied continuously, supported completely, and backed by an industrial system that turned warfare into applied manufacturing. The Soviet Union learned this lesson and applied it. Their 34 tank followed similar principles: good enough, producible in massive quantities, maintainable under field conditions. They built over 80,000 34s. Like the Sherman, it wasn't the best tank technically. Like the Sherman, it won through availability and logistics. Germany never learned this lesson. Even as the war turned against them, German tank designers kept pursuing technical perfection. The Tiger II, introduced in 1944, was arguably the most powerful tank of the war. It was also a logistical nightmare, mechanically unreliable, impossibly heavy, and built in quantities so small it had virtually no strategic impact. Fewer than 500 were produced. 500 Tiger IIs versus 50,000 Shermans. The numbers tell the story. Hauptmann Klaus Richter survived the war. In 1946, he was interviewed by American military intelligence officers researching German perspectives on Allied equipment. When asked about his experiences testing War Daddy II at Kummersdorf, he said something that appeared in classified reports but didn't become public until decades later. The Sherman's multiple engines weren't a flaw. They were a warning. They told us you had so much industrial capacity you could build 5 completely different versions of the same tank simultaneously. That's when I knew, though I couldn't admit it then, that we would lose. Not because your tanks were better, but because you could make more tanks than we could make shells to. Destroy them. That realization, that moment of understanding, represents the true story behind the Sherman's 5 different fuel types. It wasn't about the engines. It was about what the engines represented. A nation that had mobilized its entire industrial base for war. A nation that had solved the problem of military logistics not through careful planning and standardization, but through massive overcapacity and built-in flexibility. A nation that understood modern war was won in the factories of Detroit, as much as on the beaches of Normandy. The German tankers who tested captured Shermans kept hoping to find a fatal flaw, some vulnerability that would explain how to beat the American war machine. What they found instead was something more disturbing. The Shermans were just good, not excellent, not perfect, just good, reliable, maintainable, available, and good multiplied by 50,000 beat excellent multiplied by a few hundred every time. Today, when military historians study World War II tank development, they often focus on technical specifications, armor thickness, gun penetration, speed and mobility. These matter, certainly, but they miss the deeper lesson that the Sherman's 5 different fuel types teach us. Logistics wins wars. Industrial capacity wins wars. The ability to deliver adequate equipment in overwhelming quantities, supported by supply chains that just work, beats superior equipment in limited quantities with fragile supply chains. The Sherman wasn't the best tank of World War II. The 34, the Panther, the Tiger, various models could claim technical superiority in specific areas. But the Sherman was the right tank. It was the tank that could be built fast enough, shipped globally, maintained easily, and replaced instantly. It was the tank that matched American industrial philosophy: engineer it well enough, build it in massive quantities, and support it completely. Those 5 different engines, those multiple fuel types, they weren't signs of confusion or poor planning. They were signs of a nation that had figured out how to wage industrial war at a scale unprecedented in human history. They were signs of a military-industrial complex that could adapt, improvise, and overwhelm through sheer productive capacity. German engineers at Kummersdorf never understood this until it was too late. They kept looking for the perfect German solution. One perfect engine, perfectly manufactured, perfectly supplied. The American solution was messier. 5 good engines, manufactured wherever capacity existed, supplied through flexible logistics networks that could adapt to whatever was available. Messy, imperfect, undefeated. The lesson extends beyond World War II. It applies to any conflict where industrial capacity matters. Modern militaries still wrestle with the question: do you build a small number of highly advanced, specialized systems, or do you build larger numbers of good enough systems that are easier to maintain and replace? The F-35 fighter program echoes the German approach: technically sophisticated, incredibly capable, complex to maintain, expensive to produce. The Sherman philosophy would suggest building something simpler in larger quantities. Which approach is right depends on the nature of future warfare, but history suggests that betting against logistics and industrial capacity is dangerous. The Sherman's 5 different fuel types also teach us about adaptability in large systems. By designing around standardized interfaces rather than standardized components, the Americans created a system that could absorb disruptions. When one supply chain failed, others continued. When one factory was damaged, others compensated. Redundancy wasn't waste, it was resilience. In modern terms, this is like having multiple vendors for critical components, using open standards rather than proprietary systems, and building flexibility into complex supply chains. The principles remain valid. Finally, the Sherman story reminds us that good enough is often better than perfect, when time and scale matter. Perfect tanks that arrive too late don't help. Perfect tanks that can't be maintained in the field don't help. Perfect tanks that can't be replaced when destroyed don't help. Good tanks that are available now, maintainable with available skills, and replaceable from ongoing production, those win wars. The German tankers who tested captured Shermans learned this lesson the hard way. They wrote detailed reports praising the Sherman's reliability and critiquing its armor and firepower. They recommended German industry adopt American manufacturing techniques. Their recommendations were ignored. German industry continued pursuing technical excellence until the factories were bombed and the workers were gone. By the time German commanders understood what those 5 different fuel types really meant, it was May 1945, and the war was over. Thank you for watching. For more detailed historical breakdowns, Check out the other videos on your screen now, and don't forget to subscribe.